My name is Nicholas Short, and this is my presentation on the EE368 Lab 7 Part A, otherwise known as Deliverable 2. So the whole premise of this lab was to understand how windowing and filtering affects an input. In this example, we were using the T wave as our direct input. And using the filter that was derived in the pre-lab through what was defined as a 7-tap filter, and using the digital filter, we were able to show how the signal is supposed to respond to the filter and to a degree of windowing. The setup started with taking the digital filter file that was provided for us and being able to understand how the initial wave responds without any without the 7-tap filter. And the result of that is kind of your base point, like of what we're supposed to see. And then what we're comparing it to is after we've applied our 7-tap filter within the code, how does it alter the output? How does it change what's expected? What is it supposed to put out? Is it supposed to improve the sound? Is it missing sample values, or is it causing a little bit of aliasing? So using a previous code, we were able to find both the previous spectrum, and then using the newer code, we were able to find the current spectrum. And the results came out to be in the way that the left side is the pre-filtered signal, the raw T-wave signal put in a live spectrum. And then the result on the right is a filtered signal. And there is clearly some visual differences. There is the peak frequency, otherwise known as the lead harmonic, that seems to be very, very close, very, very similar in that one distinct point. But as the frequency increases, the filtered spectrum starts to flatten out a lot sooner, but also have peaks towards the end, while the original one has high peaks towards the 2000 hertz frequency range, but bottoms out very, very quickly. And what the discernible difference means that the filtered response is taking up a frequency that was missed that was coming from the signal that wasn't being left out because it was not filtered. So one big thing to draw is that magnitude means that there was a sound there that was being lost due to, say, white noise or something outside within the recording of the original file. And the filter helps to account for any of those losses or aliasing that's occurring between the white noise and the original audio or the wave that's supposed to be coming in. And it makes the spectrum more clear, as it allows it to kind of decrease at an expected rate rather than decrease, kind of have a bump towards the beginning and then flatten out all of a sudden and not account for anything throughout or changes throughout the entire spectrum. And throughout that whole duration, we're able to define what kind of filter it is, and also how the actual expected behavior, what we're supposed to hear, with better clarity, and as well as audio consistency with no chopping or indistinct cutoffs, unlike in the original unfiltered results. And that's it.